I selected for my topic this evening the title, Astronomical Darwinism. I don't think I've ever seen that term before, so maybe I'm the first to make it up. So you were here when it was coined, perhaps. But I mean by that how evolutionary thinking has filtered into the field of astronomy and affected it quite a bit. And I would guarantee you if I threw out the word evolution and asked you to tell me what science, mention a science, most of you would say what? Biology and geology, wouldn't you? You wouldn't think astronomy necessarily. And that's kind of a problem. Most people aren't aware of how much it's come into play. My father was a very simple man. He finished the 8th grade in the one-room schoolhouse of eastern Kentucky. I descend from 5 generations of Kentucky hillbillies. All right, and my father was a simple man, as I said, but he read a bit, and he read National Geographic the last, for about 10 years in the 1980s primarily. And I was in grad school still at the time. I went home to see him, and he had read an issue they had on astronomy. It was talking about billions of years and evolution and all that sort of stuff. And he was fascinated with it, but he said, I'm going to ask you something. In astronomy, do they talk about all that evolution and stuff? And I told him, yeah, they do. And he was quite surprised because he thought the problem was in biology and not in astronomy. So I want to share with you some of the broad areas of problems there. We really have 2 explanations of how we got here. Either we have evolution, which I'm going to define to be a purely natural, purely physical process. Or we have creation, which I define as being reverse of that, a supernatural process. Now, if there's a biologist here who happens to be an evolutionist, they're probably going to jump up and down and argue variation in gene pool frequency or things like this, some sort of definition. But I'm trying to keep this just as broad as I can because it applies not only to biology, but also, as I said, to geology, astronomy, even to the so-called social sciences, history and law, almost economics. Almost every human endeavor has an evolutionary basis to it today. People have brought that in. And really, if you look at these 2 definitions, you can see very clearly that the 2 are mutually exclusive. Now, there are people who attempt to say, well, evolution was God's method of creation. We call these people theistic evolutionists. And I've known theistic evolutionists, people I didn't doubt their salvation. But on the other hand, I don't believe they're right on this issue. I think they're very wrong. Skip in the previous presentation shared with you a lot of the theological problems that you have in believing such a thing. Again, I think you can be born again and believe evolution, but I think you can also be very wrong about these things, and it does affect and color your world very much so. So if you really understand what evolution is trying to do, explaining everything on basis of purely physical natural processes, you can see that's completely incompatible with what Scripture tells us. And again, we tend to think of biology and geology, but it's also affected astronomy as well. Now, for sure, Charles Darwin did not address astronomy. I'm not aware that he ever did. He was worried about the origin of species and the descent of man. But it has affected those other sciences. And we call that Darwinism. Now again, Darwin actually didn't even invent the idea of evolution. That goes back at least to the ancient Greeks. Because you see, if you don't have a transcendent creator who made things, then how else did it come about? And if he hadn't come up with his theory of evolution, then somebody else would have very soon. So I think many times Darwin, whose bicentennial we're celebrating about this time, or noting I should say, is perhaps a bit overrated, but where it is. Darwin has affected us all, and so we call it Darwinism, just a belief in evolution. And many times people try to dismiss we creationists by saying, well, believing in creation or doubting evolution is like doubting gravity. But there's a problem here because we use science in 2 very different ways. One is operational science. That's science that's testable in the here and now. We can test various theories of gravity, for instance. And much of astronomy is dealing with the universe as it now exists. Nothing about origin. And the other type of science is what we call historical, if you will, origin science, questioning how things came about, how they developed over time, those sorts of questions. So my complaint here, my argument is not with all of astronomy. It's only with the question of where things came from. And I would submit to you that probably 90% of astronomy, as much other science, really doesn't come down to origins. It comes down basically to description of the world as it now exists. And I'm going to share with you very briefly tonight 4 broad areas that I can identify in astronomy dealing with this evolutionary idea. One is the Big Bang, which is the modern theory of the ultimate origin of the entire universe. And then there's the question of how galaxies and stars came about. And then working a little later in time, you have this question of chemical evolution. I'll define that for you in just a little bit. And then we have the formation of the solar system, including the Earth and the other 7 planets in the solar system. And I'll take these one by one. Okay, first of all, the Big Bang. What is that? Let me define that. By the way, I'll be talking about that tomorrow at 11:30, so you have to come back to get a more full treatment of this whole topic. But simply put, the Big Bang is the idea that the universe suddenly began 13.71 billion in 4 years ago. I say in 4 years ago because they announced this date 4 years ago, so I have to keep adding the time to it. And this sudden appearance of the universe was a bit controversial at first when first proposed, but back in the mid-1960s they discovered this thing called the cosmic microwave background, or the CMB for short. And that microwave background was a prediction made by the Big Bang theory. And when it was discovered in the mid-60s, that really won the world over pretty quickly. By the late 60s, almost everybody believed in the Big Bang. And the Big Bang is not just the beginning of matter, but it's also a beginning of matter, space, energy, and time. Sometimes people ask, well, what was here before the Big Bang? Well, that doesn't make any sense within the model, because you see here denotes space, and before has something to do with time. And so to ask what was here before there was space and time makes no sense. It truly is the beginning of everything, and it's basically a denial of a transcendent creator, a creator outside of space and time as well. But some people do see within the Big Bang model theism. They say, well, there was a beginning, so therefore there had to be a beginner, a creator, to make it all take place at some point. I think they failed to see some of the direction that astronomy has taken in recent years and cosmology has taken, because there are many attempts today to explain the origin of the universe apart from a beginner, a creator. They have this idea that the universe began in a quantum fluctuation. One cosmologist famously said that the universe is just one of those things that happens from time to time. So sort of accidental sort of thing. That's the ultimate evolution. It really isn't biological evolution, the belief that life just accidentally arose and into a series of accidents, of mutations, and random things changing and natural selection, we finally happen. We're the ultimate accident. But even cosmologists today are saying that the universe began as the ultimate accident at some time in the past. And this is an image put together of the Kobe experiment almost 20 years ago now, showing the entire sky in this cosmic microwave background. And the red and the blue and the yellow and the green offer different temperatures, slight variations of the temperature. This thing is only a little over 3 Kelvin. That's just a few degrees above absolute zero. And real temperature, it's almost 450 degrees below zero. It's very cold. But there's a lot of energy there, actually. And you've got slight fluctuations in the temperature on one part in 100,000 showing up. It's very smooth, little tiny bumps. And those little different colors there are showing you the different bumps, warmer and cooler areas in that background radiation. And this is supposed to be the great evidence for the Big Bang having taken place a long time ago. Now, once the universe comes into existence, this big accident takes place. Then you have matter expanding over a long period of time, and after maybe a billion years or so, you begin to coalesce material into groups that subfragment into stars, and you form eventually stars and galaxies out of this. Stars, galaxies, this is one particular one. This is called M104. It's sometimes called the sombrero galaxy because some exposures of it look a little like sombrero. Contains a couple 100 billion stars. You can see a lot of dust lying along the plane of the galaxy, bulge up here. Very beautiful galaxy. A couple 100 billion stars located in that. We live in a galaxy similar to this called the Milky Way galaxy. These are just two of maybe 100 billion galaxies in existence. We have a big universe, a big creation. And galaxies tend to clump together in groups, what we call clusters of galaxies. This is the Coma star cluster, the Coma galaxy cluster. We have a couple of stars here that are foreground stars in our own galaxy, but you'll see across the photograph a number of little faint smudges, little pinwheel shapes and little elliptical shapes. Those are all galaxies. And this one cluster, the Coma cluster, contains about 1,000 galaxies. And there are tens of thousands of mapped and named clusters of galaxies. And it just goes on and on and on. So you have most stars within galaxies and most galaxies within clusters of galaxies. So we see a huge hierarchical structure in the universe from the very big down to the very small. Well, how does galaxy formation come about? Well, you remember those little bright and hotter and cooler regions in the cosmic background, microwave background I showed you the photograph showing those. Well, the theory is that early on in the universe, very beginning, when the Big Bang first happens, very hot, very dense, there are very slight variations in density. And those more dense regions act as gravitational seeds. The gravity is a little stronger here because there's more mass, and so it begins to attract more mass to it, and this thing begins to grow, become more and more dense, and it does so at the expense of nearby other regions that are less dense. So the more dense areas begin to grow in mass, and the less dense regions begin to lose mass, and this then produces all of those big clusters of galaxies which fragment down into galaxies, which fragment down into stars. And that's what we see today. And those bumps, as it were, in the microwave background is showing you where these things supposedly took place. For a very long time, the theory has been that the galaxy begins to form, big cloud of stuff, and then stars begin to form out of that big cloud of gas. But in recent years, there have been some astronomers who begin to argue, well, maybe stars formed first, and then they aggregated into galaxies. And I find that interesting because it's just been dogma for so long that it went the other way around. Now, still, the majority opinion is galaxy structure came first, but some astronomers are arguing the other direction. A lot they're not sure about. They're sure it came about naturalistically, but they can't agree on just what direction or process that took. Again, it's like biological evolution. There are different theories about how it takes place. They all agree, all the biologists, that it happened, but I should say most biologists agree that it happened. They can't agree on how it happened. So we see that theme again and again throughout science. And another interesting thing is when we look off at great distances, I showed you the Sombrero galaxy. It's really only about 30 or 40 million light years away from us. That's a light year being how far a light would travel in 1 year. That's a pretty close galaxy. The Coma cluster is a few 100 million light years away from us, and that's a pretty close cluster, actually. And as you go farther and farther out into space, first a few million, then maybe 100 million, then a billion, and then maybe 3 billion light years, you're looking farther and farther out, and presumably to an earlier and earlier period in the age of the universe. And you would expect that as you looked at great distances, the galaxies would be infant galaxies. They'd be very young. But what we find is no matter how far out we go, the galaxies pretty much look like the same galaxies nearby to us. It would be as if you looked at pictures or saw individuals who are supposed to be youngsters or babies, and they look like me, all right? It's just not the sort of thing you would expect. There is only the slightest systematic difference in color. More distant galaxies tend to be bluer than nearby galaxies. But the structure we see is identical, and the chemical composition is surprisingly similar. And so we don't see real evidence of that evolution supposedly taking place in all this. You all heard of Edwin Hubble, haven't you? You all heard of Edwin Hubble? The Hubble Space Telescope's named after him. I'm going to talk a little bit about him tomorrow as well. Edwin Hubble was a very important astronomer in the first half of the 20th century. He was really on the crest of American astronomy becoming dominant. European astronomers had dominated before, and he was part of that crest of this. He came up with a classification scheme for galaxies. He found that some galaxies were shaped like ellipses, and he called these elliptical types. And the E stands for elliptical, and the numbers stand for how flattened that they are. And then you have spiral galaxies. And I showed you a photograph of one before. These are spiral galaxies. The arms get less tight, and the nucleus gets smaller as you go from A to B to C subtypes. That S stands for spiral. Over here you have the barred spirals. These are just like the other spirals, except they've got a bar running across the middle. I always thought those were pretty galaxies. I think those are really lovely. And by the way, for many years we thought we lived in a normal spiral galaxy. We now know we lived in a barred spiral galaxy. And I like to tell people, I don't know about you, but I feel better about myself living in a particularly beautiful galaxy now. So we have the barred spirals, and again, the nucleus gets smaller as you go from A to B to C. By the way, SB stands for spiral, comma, barred. And this is called a tuning fork diagram because it's shaped like a tuning fork. And usually anymore when you see this discussed, it's just simply showing the classification scheme that he had. But when Hubble proposed this back in the 1930s, he meant something very different by it. He thought that galaxies evolved from the E zeros over to here. It then split into one of the other two types, and the arms unwound. So he thought evolution of galaxies went from left to right. Other astronomers said no, they evolved from right to left. Now, do you see that they both can't be right? Well, it turns out the last 40 years they've decided that neither of them are right. They think now if a galaxy starts off as a particular type of spiral, it generally stays that way. So there's no evolution from one type to another in general. There are some special catastrophic cases. So again, these speculative ideas about how galaxies develop, and they keep changing all the time. I'm sure in another 40 years, the understanding of galaxy structure and evolution will change dramatically once again. So we get these changing ideas, not sure I want to stick with that. Related to galaxy formation is star formation. Now, we can do a little calculation. Excuse me. Assuming that the sun gets its energy from thermonuclear fusion of hydrogen into helium, which, by the way, there's pretty good evidence to support that now, we could do a calculation to show that the sun would last for maybe 10 billion years maximum. 10 billion years maximum. Doesn't mean the sun's that old. It simply means it could last that long at the rate it's doing things. Notice that this is quite a bit less than the 13.71 billion year age of the universe. We can do similar calculations for other stars, and we find that many other stars have ages less than 13.7 billion years too. This kind of reminds me of Psalm 102. It speaks about the earth and the heavens being made by God, and yet while God lasts forever and doesn't change, they will wax old like a garment. They'll wear out. So that much at least is consistent, without putting numbers on it, at least consistent with what the Bible already tells us about stars, that they don't last forever. The point is that it seems that these stars can't be primordial. If the sun could last a maximum of 10 billion years, and if the universe is 13.7 billion years old, the sun would have died out almost 4 billion years ago. So obviously, we need to make new stars someplace. If you believe in billions of years, you must have stars being born somewhere. Where can you get these stars being born? When we look out into space and we see vast clouds of gas and dust in space. Huge amounts, as it turns out, of material in these large gas clouds. Now, when I say big gas clouds, they're pretty thin. A really dense cloud in a cubic centimeter, a little bigger, a little smaller actually than a sugar cube, would contain about 1,000 atoms. Anybody have any idea how many atoms or how many molecules are in a cubic centimeter of air that we're breathing right now? Anybody? It's on the order of 10 to the 18th power. 1,000 is 10 to the third. So the air you breathe is something like 1,000,000 billion times more dense than the densest of these clouds. What they lack in density, they make up for in volume. They're actually better than harder vacuum than we can produce on the Earth, but it does make it up in volume. The composition we measure in these gas clouds is very similar to that of stars. About 75% of the universe is hydrogen. About 24% helium. So they reason if the compositions are very similar and you've got lots of material out there in space, what would happen if you could compress a gas cloud down and get it down to the size of a star? Well, what happens? You've taken high school science, physics, chemistry, something like that perhaps. When you take a gas and you make it smaller, what happens to the density? It goes up, doesn't it? What happens to the temperature? It goes up. And whereas these gas clouds are very thin and very cool, stars are very dense and very hot. If you can compress them down, voila, you turn a gas cloud into a star. And most astronomers seem to think that's where stars come from. And so you compress them down. Maybe gravity will do this, is the point. Well, there's a problem. Gas clouds are stable against collapse. They have very feeble pressure. They have very feeble gravity. If you compress the gas cloud just a little bit, the pressure will tend to re-expand the gas cloud, and you can't really get it to compress down. In order to get gas clouds to form stars, you need to jump start them somehow, give them a jolt. And there have been several mechanisms to do that, and one of the most common is to appeal to a supernova explosion. You have a supernova go off, boom, it explodes. Here's the gas cloud, the shock wave. And the material coming off the supernova can be going like 2,000 kilometers per second. In real speed, it's like 1,600 miles per second. You could go from here to the west coast in, what, three seconds or so? Anyway, it just comes along, slams into the side of this gas cloud, and compresses it down to form a star. Now, what's a supernova? Anybody? It's an exploding what? It's an exploding star. So where did that star that exploded come from? Well, there was a supernova over here that exploded, and the shock wave compressed the gas cloud to form that star. Well, where did this supernova come from? Well, there was you see what's going on here, right? What kind of problem do we have here? We have a chicken and egg problem, don't we? All right, it's a chicken and egg problem. You need chickens to make eggs and eggs to make chickens. And by the way, this is supposed to be a really complicated question. An imponderable, a question that has no answer. But I would submit to you that it very definitely has an answer. All right? So I want you to think about it just for a moment. Which came first, the chicken or the egg? Okay? This is not a hard question, is it now? All right, everybody that thinks the chicken came first, raise your hand. Okay, most of the hands go up. I guess I want to ask for the egg. Congratulations, if you raised your hand, you're a creationist. Because you believe that God created some chickens who then laid eggs to make more chickens. If you're an evolutionist, you have to believe some non-chicken laid an egg that then hatched into a chicken. Now, I'm not trying to be funny here, folks. I mean, that really is what you have to believe, all right? So there's a real answer here. You know, creationists believe the chicken came first and the evolutionists believe the egg came first. Now, there are other explanations of how gas clouds can be compressed down to form stars. I've given you one of the easier ones to see what the problem is, but I've looked at them, and almost every one of them requires that stars first exist. In other words, you have to have stars to beget stars. There's one mechanism out there that doesn't. It simply hypothesizes, oh, you love this, it hypothesizes that early in the universe, some unknown mechanism caused a bunch of stars to form. And this is science. This is science. No data, no observations, just, hypothesize that something happened. An unknown, non-repeatable, non-recurring, not visible today process caused all this. It's amazing how science has changed in my lifetime. Well, this is a very famous photograph you probably saw a few years ago. This is taken with the HST, the Hubble Space Telescope, showing what they call pillar structure, pillars inside of what's called the Eagle Nebula. And this was shown to be, these are the gas clouds here and some darker regions right here. And the explanation of this photograph was that you were getting compression of the gas cloud there to begin star formation, and some of these denser regions were one day going to produce stars. And it had a really nice long explanation about all this, but all you had was a photograph. The one you're looking at right now. There are no measurements, no changes being observed. It's just a photograph, and from this photograph they put together a whole story, came up with a whole just so story of what's going on. Here's another one, a star-forming region in a small satellite galaxy of the Milky Way, a thing called the Large Magellanic Cloud. And these are supposed to be really young stars, and some of the dust, you see this blue glow is dust nearby, and you can see some of the dark regions, those are dust, there's some gas mixed in, and that's supposed to be the environment where these stars form. And if you start looking up some writings, some papers and discussion of star formation, it will show you all sorts of photographs like this with all sorts of explanations. But when you really dig deep and start looking at it, they're simply interpreting the photographs a particular way. There's not a whole lot of data here to work from, a whole lot of rigid science to work from. It's interpretations of what we see in terms of the evolutionary paradigm, which then, of course, proves the evolutionary paradigm. Chemical evolution. We have the Big Bang beginning with, starts the universe with hydrogen, helium, and just a little tiny bit of lithium. So little lithium, it's hardly worth mentioning. Now look around you. How much helium do you see? Well, you can't see the helium. Okay. How much helium is there around us? Well, not a whole lot, as it turns out. Helium wasn't even discovered on the Earth until about 120 years ago. Helium's not a major player on the Earth. And hydrogen, well, you've got your body made out of 75% water, which is H2O, but only about 10% of the water by mass is actually hydrogen. The other 80-90% is oxygen. Your bodies are primarily made out of that water, which is mostly oxygen, but also it's made out of carbon and nitrogen, calcium in your bones, iron in your blood. Actually, there's several dozen trace elements, none of which are hydrogen and helium. Look around the room. You've got wood made out of the same carbon, nitrogen, and oxygen, fibers in the carpets, calcium in the limestone and the concrete. You have steel beams in here made out of iron, and it goes on and on and on. And according to this, none of this was produced in the Big Bang. So where did the iron in the walls around us, the calcium in our bones, all these things, where did they come from? Well, the answer we're given is that thermonuclear reactions power stars. And again, I think there's evidence to support that the sun is fusing hydrogen into helium deep in its core. Well, it still just gets you helium, right? Well, later stages of development stars go through as they get towards the end of their lifetime. You can fuse some of the helium into carbon, and later on some of that carbon into oxygen, and some of the oxygen into help me out here, element number 10, it's neon, okay? You go even numbers all the way up through iron, and then you can have some other processes that take place. Fascinating thing, I took a couple of courses in grad school on this, where we spent a whole semester just going through the nuclear physics of all these sorts of things, but you have a lot of pathways. We've got what's called the R and the S process elements. It stands for rapid and slow neutron capture. And you eventually produce some of these heavier elements as stars are aging and producing energy from these different reactions. And then the matter is ejected from these stars, sometimes through a supernova explosion, which in turn creates other heavier elements, what I call the transferic elements. heavier elements like silver and gold, lead, uranium, things like this. And this then goes out into space where it mixes with the gas that's out there. And then you form new stars out of that. And they continue the process of creating heavier elements. And then they blow up and they spew the material out in space. And they mix with other stars. And they keep doing this, repeating the process over and over and over again. And according to this theory, the universe existed for 9 billion years before the sun and the earth came along. So the sun and the earth are pretty Johnny-come-lately on this, aren't they? And we are the product of at least 9 billion years of chemical evolution taking place in the stars. The late Carl Sagan, when he talked about this, used to mention that we're made out of stardust. We're made out of stardust. You know, it's real easy to go pantheistic here, right? You could worship the stars because that's where we came from. If you really believe this, the ancients who worshiped the stars weren't too far off the mark now, were they? What goes around comes around, I suppose. Well, a guy named Walter Baade, back, it's been at least 50, probably 60 years ago now, he noticed some differences between stars, several differences dealing with motion that they had. It was a big thing, but other things, subtle compositional differences. I could list 6 different ways or so that they're different. I won't do that. I'll just give you a couple. But they're called stellar populations. And he divided up what we call population 1 and population 2. And population 1 stars are high in metals. Now, when it comes to chemistry and astronomy, it's pretty easy. We have hydrogen, helium, and everything else. And everything else we call metals. Now, when you think about that, that's kind of a gross overstatement. Nitrogen, carbon, oxygen, they're not metals. When you look at the periodic table, almost everything outside of hydrogen, helium is. Almost everything to the left is a metal. So if you call these other 80-something elements metals, you're not too far off the mark. So we call these collectively metals. And population 1 stars are relatively high in metals. They have 2 or 3% of their mass being in the heavier elements, heavier than hydrogen and helium. That's because these are younger stars. They were created or evolved more recently, and they've had those many successive generations of chemical production taking place. Then you have population 2 stars, and these are older stars, and they're very low in metals. Some metal-poor old stars, population 2 stars, have 1/10,000th the amount of heavier elements that a population 1 metal-rich star would have. And then you have population 3 stars. Remember, Baade talked about population 1 and population 2, and incidentally, again, his things he noticed about them had nothing to do with age at first. It was later on they interpreted it that way. Population 3 stars are stars with no metals, and the reason why they have no metals is because they would be primordial. They would be primordial, and these stars formed before there's any heavier elements at all, just hydrogen and helium, and they would be the very first ones to start producing some of the heavier elements. And for 30 years, people have been looking for population 3 stars, and they've never found any. And you see today, they say when stars form, most stars are low-mass stars which have very long lifetimes, much longer than the 13.7 billion year age of the universe. And so you would expect that if the primordial stars had any kind of resemblance to the supposed current star formation rate, that you would have a lot of low-mass stars that should still be around because their maximum ages are far older than the universe's age, supposedly. But you don't see any. So how do they explain that? Well, again, I talked about that unknown process that started the first stars. That unknown process also only made them high-mass stars. Isn't that convenient? It fits the data, but where's the evidence? In science, you're supposed to have evidence for things. This is just simply a just so story. Again, in evolution, doesn't matter if it's in astronomy, biology, wherever you want, you get just so stories telling you how these things could have happened, might have happened, those kind of things. And then finally, we have the solar system formation. I mentioned that before. about how the solar system formed, a Johnny-come-lately 9 billion years into the alleged age of the universe. Again, you get this cloud of gas and some dust that compresses and goes down to form the sun. And some of the material doesn't fall into that central condensation to form the sun. Instead, it flattens out into a disk. And out of that disk, the planets and the satellites and so forth form. They do this by coalescence. What happens is some of the little microscopic particles begin to collect and stick together. And I got a howl there because we really don't know how. People suggested static electricity and little organic gunk that coats the little pieces, and they start sticking together like Post-it notes, things like that sticking together. And these things slowly build up big enough until gravity becomes large enough to then continue the process of forming planets, satellites, and asteroids. And again, you start reading this stuff in the literature, and you get a lot of perhaps, maybe, could have, might have, those kinds of things. And Charles Darwin did that a lot in his Origin of Species. Hundreds of times he said could have, might have, all sorts of couch terms of possibilities, but no definite sort of answers being given. And then finally, you build up the planets, and we have two types of planets in the solar system. The first four, Mercury, Venus, Earth, and Mars, we call terrestrial, means Earth-like. Again, there are about 7 or 8 ways that they're different from the outer planets. The next 4 are called the Jovian, that means Jupiter-like. These are very large planets. Jupiter has a lot of mass, the other Jovian planets do as well. They're also very large. They have low density because they have a lot of lighter elements found in them. They have rings, they have lots of satellites, so there's several different ways they're different. But the big thing is they're big. They're big and they're massive. Now, the theory is that when the sun started to flare up, it heated up the inner solar system, blew out all the lighter material, the hydrogen and the helium, things like that, and cleaned it out. So all was left was a solid material. Isn't much of that. It's only a few percent anyway of the sun's mass, remember? And so you have very small but dense planets. Very far from the sun, you retained a lot of the heavier elements. And this then allowed for holding on to those, so you get very massive planets far from the sun. They worked out this theory years ago on how this happened. And you would expect then that in general, small planets, rocky planets, form close to stars, and Jovian planets form far from the stars. Well, in the last 15 years, we've had quite a search for extrasolar planets. And I must say, that these are planets, by the way, outside of the solar system. They're orbiting other stars. And when the first reports came back in the 1990s about this, I was skeptical. I was really skeptical. But about 8 or 10 years ago, a couple discoveries came forth that really convinced me. I think the technology works. It's very difficult to measure these, observe these things. You basically get it by looking at the motion that the planet induces upon the parent star. As the moon goes around the Earth every month. Well, why does the moon go around the Earth every month? Thank you, gravity. All right. Now, Newton's third law. Everybody remembers Newton's third law of motion is what? For every action, there's an equal and opposite reaction. Very good. As the moon goes around the Earth every month, what does the Earth do around the moon? It goes around the moon too. So the moon's doing this and the Earth's doing that. The one that does most of the moving is the moon because it has less mass. As the Earth goes around the sun every year, the sun also goes around the Earth. Now, since the sun outmasses the Earth by a factor of 1/3 of a million, it doesn't move too much, but it does move. So if you look at a star that has a planet orbiting around it, as the planet orbits around the star orbits around the planet. In the last 15 years, we've had computing ability to enable to sort through the very complex data, looking for those slight variations in motion. And the technique seems to work. And we now have more than 300 known planets orbiting around other stars. Now, why were they looking for planets around other stars? Well, they want to show that the planets are common. And if planets are common, then maybe Earth-like planets are common. And if Earth-like planets are common, maybe life like us is common. You see the evolutionary involvement here, right? And so when some creationists see, wow, 300 planets around other stars, we're toast, they get really worried. And I'm saying, wait a minute, this is good news, folks. This is great. Because what kind of planets have they found? All the ones they've found so far are very massive, and they're also very close to their parent stars. Most of them orbit far closer to the sun than Mercury does. That's not what you expect based on what we see in our own solar system. You would expect the massive planets to be far from the sun or from the star, but what we're finding is just the opposite of what we would expect. Now, for sure, we can't find, it's difficult for us to detect small planets right now. I understand this evening, NASA is launching their Kepler mission. This is an orbiting satellite that will actually look for Earth-like planets. So stay tuned. This is even while we speak going on, hopefully. Well, my conclusion I reach is that other planetary systems we found are very different from our own. And so instead of being a great boon to evolutionary ideas and a problem for creationary ideas, I find that perhaps our own Earth and our own solar system is unique. How many of you have seen The Privileged Planet? Okay, read the book or seen the DVD. It's an excellent source and excellent movie. And he talks in there a lot about the unique characteristics that the Earth has. And I think another thing we can add to this is the fact that we don't find anything like our own solar system and our own Earth out there. The evidence seems to show that perhaps the Earth is a specially designed place just for us. And you know, I've dealt with some evolutionary ideas this evening. I think I ought to spend at least a moment or two talking a little bit about some creationary ideas. And there's some frustration that I have being a creation astronomer, because we don't have a whole lot of work to work with as far as biblical information. You know, we find in the beginning God created the heavens and the earth. I think that's talking about the astronomical space. I'm not quite sure what that means when it mentions heavens there in verse 1 of Genesis 1. And then on the fourth day, it talks about the fact that God said, let there be two lights in the sky. One is the greater light to rule the day and provide light, and the lesser light to rule the night. Of course, the sun and the moon, not mentioned by name, because those were actually pagan deities, I believe. It talks about the purposes they have for being for signs and for seasons, for giving light upon the earth and ruling the day and ruling the night. And then almost as an afterthought at the end of the day 4 narrative, it says, and he made the stars also. Just hardly any mention of them at all. In Hebrew, I understand it's basically the stars also. It just, that's short. And then immediately it says in the evening and the morning were the fourth day. So it doesn't give us a lot of information to work with. As a stellar astronomer, that's what I call myself, because I study stars. And I find that a little frustrating. But it also gives me a lot of freedom, I think, to investigate and think outside the box tremendously. Already we creationists think outside the box. And I would like to leave you with a couple of verses tonight from Psalm 8. When I consider thy heavens, the work of thy fingers, the moon and the stars which thou hast ordained, what is man that thou art mindful of him? It's a good question. You know, I mentioned that our own galaxy contains a couple 100 billion stars. Taking that as an average, you get 100 billion galaxies. So on average, if they contain, let's say, just 100 billion stars, do you realize that the total number of stars is 10,000 billion? Minimum figure, by the way. And yet the psalmist also tells us that he calls them all by name. We have a very big, mind-blowingly large universe. But you know what? We've got a much bigger, mind-blowingly big God, don't we? Much bigger than that creation he's given to us. You know, the late Carl Sagan wrote a book called The Pale Blue Dot. And it was referring to the Earth, this insignificant little bluish dot that really didn't amount to much. It was a little tiny dust mote floating around in this vast cosmic sea. And he was asking basically, how important are we? Well, that's what the psalmist was asking too, right? He says, when I consider the heavens, the work of your hands, the sun, moon, and stars, what is man that thou art mindful of him? It's just what pale blue dot was asking. But a very different answer. Very different answer. What answer did Carl Sagan have? Basically, we're not much of anything, are we? And we're not very important, and that's about all there is to it. But the psalmist goes on and answers the question. He says, for thou hast made him, talking about mankind, a little lower than the angels, and hast crowned him with glory and honor. You know, we're not special because of who we are. We're not special because of what we've done. We are special because what God has declared us to be. He's made us the crown of creation. And why are people very important in God's sight? Going back to Genesis 1, how are we made? We're created in the image of God. And that makes all the difference in the world. If you believe we're made in the image of God, you're going to look at yourself and you're going to look around the people around you and you're going to look at the world as a whole very differently than if you believe we're just a cosmic accident, a pale blue dot who doesn't amount to anything in the world.